Okay, so welcome everyone to another Quantum T roundtable section. And today I'm planning to talk about a little bit Einstein-Podolsky-Rosen paradox, and I will show some slides, and in the end we we have our discussion section. Okay, so I'm sharing. Okay, so this is the slides. Okay, so welcome. Talk about Einstein-Podolsky-Rosen. Just like to start, this was a paper for 1935 that Einstein was never comfortable with the ways quantum mechanics was following. Just to everyone make sure he understands quantum mechanics and he knows uh, that the theory was good to explain the experiments that we have until then. We are in the 30s here. But he was not, he always believed that the theory was incomplete. And this paper, with the collaboration with the Boris Podolsky, I think, in Nathan Rosen, the name, he tried to show some arguments about this incompleteness of the theory. So my idea is that just give a summary about the Einstein-Podolsky-Rosen and a brief summary as well about the Bohr response for the Einstein-Podolsky-Rosen. Then we have a discussion. So okay, so let's start. Following the uncertainty principle, if two observables do not commute, we can't know the eigenvalues with maximum precision simultaneously. So when measuring one of these observables, the usual interpretation is that the wave function collapses to the eigenstate that corresponds to the value measured. And the quantity associated with the other observable, the other that was not measured, is undetermined and without physical reality. So we know that the individual terms of a superposition represent potentialities. And in this case, we can only talk about the probability of finding a certain value to this other observable. So Einstein was uncomfortable with this way of thinking about the quantum reality, and he wanted to show that this determination was not fundamental. And the quantities relative to two observables that do not commute between them would have an objective and simultaneous reality. And the conclusion about the paper, his conclusion is that the wave function did not have a complete description of the physical system. So he showed this in this paper, 1935. And to prove these things, Einstein need to attack, let's say, I don't know if it's the best word, but he wants something to oppose to the uncertainty principle, proposing experiments, like thought experiments here, where quantities associated with observables that do not commute could be measured simultaneously with high precision. And here is the paper, March 1935. And here I put some marks just to where this summary is in the paper. He say here in the abstract, in quantum mechanics, in the case of two physical quantities described by non-commuting operators, the knowledge of one precludes the knowledge of the other. I think I have questions? No. Then, first one, the description
I
of
had
reality.
just a little comment, sorry.
Oh, okay.
Ansatz is German for attack in chess and is also used in
Yeah, yeah,
mathematical physics. So maybe Ansatz would be
it's better
another
than.
attack, another translation for attack.
Okay, good. Okay, thanks.
Sorry.
And so, again, so in quantum mechanics, in the case of two physical quantities described by no-commuting operators, the knowledge of one precludes the knowledge of the other. Then either, one, the description of reality given by the wave function in quantum mechanics is not complete, or two, these two quantities cannot have simultaneous reality. And in the end, his conclusion is that if one is false, so if the wave function is the wave function of quantum mechanics is complete, if this is false, so the second is false. So we can have simultaneous. The two quantities can have simultaneous reality. So, so again here, so in summary, the authors follow the two definitions. The theory is complete if every element of the physical reality must have a counterpart in the physical theory, and if without in any way disturbing a system, we can predict with certainty, or in other words, with probability equal to the unity, the value of the physical reality corresponding to the physical quantity, to this physical quantity. So here I'll not, just to give an example, I'll not show the experiment suggesting EPR, because there is, after the paper, there was like maybe more didactic alternatives. One was proposed for Bohm in his book in the 50s. And I will use this where we use like a spin particles. That is the traditional, is traditionally teach today. And in the EPR, Einstein used like the relation of momentum and position. But here we will use like these spin particles. So very quick here, I'll not use the whiteboard today because the expression are simple. So the correlations, these we can find in textbooks. So we consider a two electron system in a spin singlet state, total spin 0. The singlet state is given by an expression like this, where we have explicitly indicate in this case, I choose like the z direction to the quantization. And just to remind here, this term here, the first term, is I'm saying that electron, let's say two electrons, electron A is with spin up state, and electron B in the spin down state. Okay, and the other this other term is electron A is with spin down state, so represented by minus sign, and electron B with spin up state. So we have this like superposition state. So suppose that we measure the spin component of one of the electrons, and there is a 50-50 chance of getting either up or down, because the composite system may be this one or the other one, with equal probabilities. So if one of the components of the electron A is shown to be in spin up state, the other is necessarily in the spin down state, and vice versa. So when the spin component of electron A is shown to be up, the measurement apparatus has selected the first term, this one. So I make the measurement and show that the electron A has spin this. So a subsequent measurement of the spin component of electron B must ascertain that the state ket of the composite system is given by this. So with certainty, if the first measurement is this one in red, the second will be this one, and this will be the composite system. So it is remarkable that this kind of correlation, so we have a correlation here, right? Because before the measurement, we have this uncertainty, that's in this case, nothing red here. After the measurement, if I measure the first one, like the A, electron A, with a spin up, so I know when I measure the electron B, it will have like spin down. So we have correlations. So it's remarkable that this kind of correlation can persist even if the two particles are well separated and have ceased to interact provided as they fly apart. There is no change in the spin states in this case. So this is a very important thing because this is a very strong correlation, right? It's a very strong of action to a distance more complex than if you think in the Newtonian theory, because in the Newtonian theory we have like this action to a distance, but it decrease with the distance, right? As far apart the let's say the two particles is, the effect is smaller. But here this thing does not happen. So it has like instantaneous correlations, and it doesn't matter how far apart the particles are. So to reply to the EPR argument, Bohm wrote a paper, 7-page paper, response to this question. Okay. So this is very brief summary about the EPR. We can discuss more after that finish here. So the paper was like 4 months after the EPR paper in 1935, with the same title. It's not wrong here. It put exactly the same title. And in summary, he admits that there is no mechanical disturbance in region B due to the action carried out in region A. He states that there is essentially the question of an influence, and here, the things that is exactly when it is there in the paper. There is essentially the question of an influence on the very conditions which define the possible types of predictions regarding the future behavior of the system, in this case, the system B. And he questions the applicability of question 2 in the EPR to the case considered. So Bohr is thus connecting the notion of physical reality only to what can be predicted about the system B, and making this prediction depends on what is done in A. In this way, he tries to conserve mechanical locality, but introduce a new type of action at a distance that in the future Einstein would call like spooky action of a distance, right? So since he attributes the term physical reality to what we know about the system. Thus, Bohr removed from the notion of physical reality the reference to the parts of nature that exist and we can or cannot know, and limited himself to only the parts that we can know. So therefore, being subject to the choice of experiments that will be carried out. Yeah, the second point. So in summary, in this orthodox interpretation of spin singlet case, returning to the spin singlet case, like in the Bohr response, Bohr was responding the EPR paper that was talking about like momentums and position not talking about the spin singlet. But this interpretation for the spin singlet case is that a measurement is a selective process. When Sz of particle A is measured to be positive, so we have this situation, then the component is automatically selected. And the subsequent measurement to the other particle B merely ascertains that the system is still in the state when measured in the first time. So just to finish, we must accept that a measurement of what appears to be part of the system is to be regarded as a measurement of the whole system. This type of response, just to mention here, was rejected in the EPR paper. In the EPR paper, they write exactly this in the end of the paper. And one would not arrive at our conclusion if one insisted that two or more physical quantities can be regarded as simultaneous elements of reality, only when they can be simultaneously measured or predicted. This is exactly in the end of the EPR paper, this part. So just to finish here, impasse of metaphysical nature was thus reached, and it took almost 30 years for this impasse to be translated into physical terms, which could be verified in laboratory. This was like the Bell suggestion, Bell inequality suggestion that could try to see who have the if this type of things that was discussing the EPR and the Bohm response, this could be like seen in a real physical experiment. So, but this was only in the 60s that Bell came to bring to us in this. And the experiments that tried to confirm this was done in the 70s. So this is some references. And I say, okay, so this is just a brief summary. We could like open for discussions. You guys are free to start. You know, someone want to give some comments? What the view about the EPR or the notion that you guys, I don't know, if everyone here is the first time that is seeing, I don't believe. I think you saw this thing before, but I see what the impression like when you guys like read or saw this for the first time. I think is a good way to start like this spooky action at distance. Okay, Visu.
Hi, Carlos.
Hi,
Can you go back at the definition of reality for the EPR paper?
You want me to share something?
Yeah, to share the second slide, so the third one where they were defining reality. What does it mean that their physical reality and the theory?
Okay, so let's share again. The second. Okay, it's the first, second.
Well, I guess then it's the next one where you were saying what Einstein was defining. Yeah, a complete theory is every element of the physical reality must have counterpart in the physical theory. I wonder whether this was before Einstein knew about the Russell's incompleteness theorem or after. Because to me, this first axiom, according to Russell's incompleteness theorem, is invalid. basically, there is always something in physical reality that your theory cannot capture. That's my understanding of the Russell's incompleteness theorem in mathematics.
It's Gödel's theorem.
Gödel's, yeah.
And the theorem says that the theory that we normally use to do arithmetic logic is in fact incomplete.
I believe that Gödel's theorem was in the late 40s, so Einstein would not have known about it.
It was in the early 30s actually.
Oh, it was? Okay, what am I thinking of 1949 then?
Maybe.
Sorry.
Yeah.
But yeah, it would be interesting to put together a timeline. So maybe I'll make a note to do that. Thank you. Thank you, Barry.
Yeah.
Yeah, so I don't know if he would know about the theorem.
I bet he would. He was buddies
Yeah.
with Gödel.
Oh, yeah?
Yeah, now I don't know when Gödel arrived at the Institute for Advanced Study, but I would imagine that even before Gödel arrived, again, we have to look at the timeline, that Einstein was familiar with the result.
Yeah. I need to check the theorem, actually. I just heard about, but I never really studied. Diego, welcome.
Hello.
Hey, how are you?
Good, thank you. I'm a little bit confused about the relationship between Gödel's incompleteness theorem and the definition of physical reality. I'm not sure how the two are related to each other.
Yes, it's back to me then trying to explain my viewpoint in this. And that's why I was asking Carlos to show the slides, because Einstein was assuming that for anything in the physical reality, you can map it to your physical theory. And basically, if you apply the Gödel's theorem, you'll say, well, you would never be able to complete such a mapping. There will be always something in the physical reality that cannot be completely mapped to your physical theory, because you build your theories usually on axioms, and all mathematical theories have some incompleteness.
Not all, but
Yeah,
a lot of the
Only if the axioms include the axioms of piano arithmetic. So there are axiom systems which are complete, but an axiom system, or I shouldn't say complete, decidable, but an axiom system, let me say strong enough, you misuse the term, an axiom system which contains the integers would be incomplete, because Gödel showed that there are undecidable theorems in arithmetic. So it's the question in terms of physics would be, how does physics relate to the integers? I mean, do the integers have physical reality, or vice versa?
But isn't that the whole point of the quantum physics, where things are discretized?
I'm not so sure about that, because maybe you could make a giant state machine with like Planck distance sized little subspaces and some enormous finite number, and this would all take place in that in a finite state machine with a a ridiculously high number of states.
Yeah, but then since it's finite, there is always one extra state that is not in your machine.
No, if it's finite, they're all reachable.
You mean if the reality is finite?
Yeah. I mean,
But
this is
if
just
it is not, this is just approximation.
yeah. That was just a ridiculous thought experiment to show that the relationship between finite and math and physics might be a little subtle.
Yeah, I agree, and of course that there is a possibility that one can always try to construct this as limiting cases. I mean, all these kind of states that seems to be outside of your initial space, then you may try to include them through completeness as a sequence of trying to approach them. But then this becomes a little bit more complicated, and it really requires to look at specific examples.
Yes, that is true. And in fact, my idea of the finite state machine kind of comes from the math of approximation, like finite element method.
So, Vissa, I think what you're saying is that we can't expect a theory to be complete in the way that it's defined on that slide.
Yeah, in the usual way we built our mathematical models and physical theories. It has to be quite sophisticated to make sure that you guarantee the completeness of your axiomatic system and so on.
I kind of read this a little differently, and it may not be the way it was intended. To me, being not omnipotent, any physical theory is only concerned with the things you care about. And there'll always be something outside of any physical theory that you don't care about. And then from that perspective, a complete theory is one that handles the things you care about. As opposed to a metaphysical idea that it's going to handle everything everywhere all the time. There'll be no exceptions. It's just,
yeah. And I think it kind of makes sense, and it kind of goes towards Bohr's approach, isn't it? Because Bohr was saying, well, let's focus on the things that we can measure, and then that's what usually I hear people think about entangled states as no, we have to view this as a whole system and not parts of subsystems of a bigger system. And then naturally there's the question, because you can turn the argument. I mean, maybe we are making it sound like a paradox. You measure A and you find that it's up, and therefore B should be down. But if you say, well, you perform a measurement, and it should be either up and down or down and up. And if you look at what you got on your instrument, then you see up, and therefore, by the rule that it should be one or the other, I mean, then it should be down. So effectively, I think this goes back to the question, what does it mean simultaneous? I mean, if you can show that there is no coordinate system where these two measurements of A and B could be viewed as simultaneous, then probably it's kind of some kind of interaction goes through. But if you find that there is a system where these two measurements are practically simultaneous in some coordinate system, then definitely there is a puzzling how is it possible in this coordinate system to have such instantaneous change of states. But if the change was down in the initial measurement, which selected the first or the second part, that there is no problem, because afterwards then you're looking at the subsystems. I mean, you already become part of direct product of states.
Yeah, and I mean the Gödel theorem was from the 30s, right? Written in like the
31, something like that.
31.
Yeah.
Yeah.
Thanks, Barry. And the EPR paper was from
35.
Yeah, thanks, Barry. So it's possible that Einstein, or likely that Einstein, knew about it.
They were both at the Institute at the time.
Yeah.
Yeah.
Thank you very much, Barry.
But the thing is that it may be, if there is no argument like this in the literature, maybe nobody ever made a connection between what was put as physical reality in Einstein and what was already known about the mathematical constructs that were at that time.
Yeah, but I think the core of the thing is like what's the definition of reality in this case? I think, like Bob said, it seems something. Reality is like in the Bohr, approach, right?
Yeah.
The things it's complete. The complete seems like, as Bohr said, like the definition of completeness in this case. So I think the theorem would not invalidate at least the Bohr thought, if I'm understanding right.
If I understand Einstein's meaning of completeness in this context, it's not the same as mathematical completeness. It's whether there are quote unquote hidden variables. So Einstein is wondering or proposing, if there are hidden variables, then if they were added to quantum mechanics, would that complete it? That's my understanding of the issue.
Yeah, because he say like the wave function is not the whole story, right? That something is missing, and this something that is missing is what was called like hidden variables that only in the 50s, like the Bohm came, he bring like a theory related to this. And then in the 50s as well, like Everett gives a theory that is not, that have these hidden variables, right? But has different interpretation, the main words.
And again, if I understand Bell's result, he only excludes local hidden variables, not global hidden variables.
Yeah.
Can you clarify?
Again, oversimplifying, if your hidden variable is like a higher dimension, and everything is local in this higher dimension, but it could project down differently to our lower dimensions of 3 space and 1 time. But the locality could exist in the higher dimension. It's actually more the other way around. You can have, say, take a sphere and project it down to the plane.
Right.
You can have 2 things which are very close on the sphere, but depending on your projection, they'll appear very far apart on the map that you draw. And so in that case, the hidden variable would be the curvature of the sphere. Again, I'm vastly oversimplifying and trying to express it in geometry.
Yeah.
But I think Shin Karo, he was approaching such similar ideas of looking at entanglement and distances, and he was talking about some of his students working on these ideas, where they were trying to derive general relativity from quantum mechanics. So I don't know how far these have gone as a project, but it kind of makes sense. The bigger question is, how do we test this? I mean,
That's I think the crux of the matter, and what's kind of interesting about the EPR thing in terms of we're living now in the age of quantum computing, that a test was performed. And I forget the name, I'm probably pronouncing it wrong. Alain Aspect actually did an EPR kind of experiment and showed that the Bell's inequality was violated. So here's a case where some philosophical interpretation arguments from the 30s do turn out to be experimentally verifiable. So that's very interesting.
yeah, I mean, I think 2015 they went to really a big experiments where two stars in opposite directions would determine what the measurement would be doing. But then it's interesting that now and then people would come up with some other ideas. I don't know how far these ideas go further, but one idea I heard about was that in Clifford spaces there is no entanglement. But I guess probably didn't fly as far as it sounds.
What spaces? Sorry.
Clifford spaces. Yeah.
I'm not sure what a Clifford space is. A Clifford algebra is a construction in a space that's a power of 2, and you fix a quadratic form. So in that sense, it's similar to an inner product space.
Yeah, it's something similar. These are planes, and how do you manipulate this kind of objects of subspaces and objects?
Yeah, thank you, Essa.
Well, I have to go to another meeting. That was very interesting and stimulating. Are we doing this every week, or it's every other week?
In principle, it's every other week. So
Okay.
in 15 days. So the idea, I'm coming and bring some team and we discuss like EPR. The next probably I'll try and maybe follow the history. So maybe the next I'll bring something about related to David Bohm de Broglie interpretation, because I think it's the next like history, and we have some sections about. I mean, just a brief summary, and then we discuss, and it's free to discuss different things.
Yeah, I like this format, and thank you very much for putting the time for organizing it like that.
Yeah, I appreciate that too. It kind of grounds the following discussion somewhere, so it's not just 2 a.m. in the dorms over beer discussion.
Yeah, but we still have time to have more interest. I mean, about Alan aspect, like I think the first experiment was in the 70s actually, but then people found that it had some problem that was not so convincing that the Bell inequalities was like really violated, and then repeat the same experiment I think in the 80s, and then again violated again, but it was still some clues because like technological problems, or maybe it's not. This is not experimentally, not so conclusive. But today it is conclusive. All the experiments, at least as far as I know, is they violate like the Bell inequalities, and yeah. Then it seems that at least with the things that was considered, it seems that this in the EPR time in the 30s. So it seems at least that Bohr it has was like right if you take you consider like the suppositions, initial suppositions, that is correct.
Yeah, something interesting I learned about recently is if you read the EPR paper, you see that it discusses the some inconsistencies about what the wave function should be, and if it's contradictory with physical realism and local realism and so on. But it also brings up this issue with non-locality, right? So that's what the experiments you're discussing are showing, that quantum mechanics is non-local, that there is no way to explain certain correlations by assuming that the interaction happened locally, right? But I recently learned about a different formalism known as the Hayden-Deutsch descriptor approach, in which apparently if instead of looking at the wave function and the evolution of the wave function in the Schrödinger picture, you actually look at the evolution of observables in the Heisenberg picture, then you can restore locality. So basically, it's a formalism of quantum mechanics that doesn't violate locality. I just learned about it, and I'm trying to understand it a little bit better, because as you know, the Schrödinger picture and the Heisenberg picture are completely equivalent to each other. So I'm still struggling in trying to understand, why is it that when you look at the evolution of the wave function, it's non-local, but when you look at the evolution of observables, you can make it fully local. But it's very interesting, because the main reason this approach was looked into is because, as you all know, there's a discrepancy between general relativity and quantum mechanics. And one step necessary to marry the two of them is to restore locality. So in this picture, you see evolutions locally. So it's an approach that can be used to keep moving in that space of trying to make quantum mechanics and general relativity work together. So yeah, I don't know much about it, but it's really interesting to see that you can actually formulate quantum mechanics fully locally.
What's the paper mean? Well,
yeah, I'll so it's called Hayden Deutsch. I'm writing it in the chat. Descriptors. I'll send a link to the paper. I wrote it in the chat. Hayden.
In terms of, in terms of timelines, I would just mention that von Neumann's formalization which showed the equivalence of the Heisenberg and Schrödinger approaches was also in 1932. So this is all happening around the same time.
Yeah, but I don't remember the von Neumann's like theorem about the another possibility of hidden variables is from the 30s as well.
Okay,
I think it's before David Bohm, I think,
yeah.
but I'm not.
1932 was von Neumann's book on the foundations. I'm not sure if his disproof of local hidden variables is in that book, but it sounds to me that it would be around the same time, if not.
I get the paper, Diego. Thanks.
Thank you, Diego.
Yeah, no problem. I think that the what's key about this is that it's not that this approach is saying that local hidden variables exist, because that's exactly what Bell inequalities disprove. What basically this paper looks into is a different formalism in which, instead of looking at quantum systems using a wave function, if you describe the system using what they call Q numbers, which are another way to represent a quantum system, you can see the evolution of these Q numbers as being fully local. Now, if you go back to the wave function formalism, that's where you have this this issue with local hidden variables.
Okay, I'll take a look. It seems to be interesting. Maybe in the future we could like discuss, like, because my initial idea, I think, is follow like the history, and then after we can like come with think more modern.
Yeah.
We are still in the 30s. We are almost 100 years ago.
Yeah, another comment about the definition of reality that I think is being used in the EPR paper is, unfortunately, I really don't know very much about Gödel's incompleteness theorem and how it links to physical reality. That part I really don't know how the two of them match together. But I think what's important is to try to define what they mean by realism. So basically, there are two ways to interpret the wave function in quantum mechanics. One is the realistic interpretation, and one is the non-realistic interpretation. What these two mean is that if you say the wave function is real, what it means is that there is an underlying reality that we could potentially understand if we keep developing new theories. The non-realistic interpretation of the wave function means that that's a question you don't even ask. You don't ask what the wave function is. You cannot never ever understand what the wave function is. All you can tell is that if you perform measurements on that wave function, you can get certain results, but that there's whatever it's encoding, it doesn't really even exist.
Yes, I think that's why Bohr's position has been described as anti-realism.
Correct. Yeah. And that was Bohr's position, that you cannot talk about position and momentum unless you make a measurement. His point of view was they don't exist unless you you perform some sort of measurement in your system. And there's some interpretation of quantum mechanics. I believe relational quantum mechanics is a newer interpretation that still works in this way, where you can't say anything about the wave function unless you put it in the context of what is it related to. So what instrument, what measurement is being performed on it. Now, on the realist interpretation of the wave function, there are two sub interpretations. One is that the wave function represents our knowledge of some underlying physical reality. So it's basically just like a probability, like in probability theory, we talk about probabilities of us knowing something about the real world. But the physical reality does exist. So that's that, and usually that's called a psi-epistemic interpretation. And then there's another one in which the interpretation is that the wave function is physically real. So it is carrying information about the physical world. It might not be all the information about the physical reality, but it's a partial information of physical reality. And that's usually known as a psiontic interpretation. And within the psiontic, if the wave function carries all you can know about it, that's called psi-complete, a psi-complete interpretation. So this is, there's many different ways in which you can interpret the wave function. And I believe what the EPR paper was discussing is that you can't say that the wave function is non-real, basically. So within all these different ways of looking at the wave function, I think what the EPR paper was referring to is that if we believe that there is a underlying physical reality, then these things are violated. So yeah, it's hard for me to align myself with the non-realistic interpretation, because to me that's basically giving up on saying it's not real, so we can never understand anything else about it. We can only understand what's happening. And I mean, it's a good approach if you're an instrumentalist and you're just trying to use quantum mechanics as a tool to do something else, right? But if you're really trying to understand how things work, I think having that philosophical viewpoint is kind of just giving up and saying, don't even try seeing if there's something underlying.
Would you say that that's similar to shut up and calculate?
Yeah, in some sense, I think. Some people would say that there are different points of view, like, for example, this relational quantum mechanics says is not entirely shut up and calculate, because I'm telling you it's more about how the wave function interacts with what's around it. But to me, it is kind of shut up and calculate, because you're not asking the deeper question of, is a wave function encoding something else that we don't know what it is yet, but we could possibly understand. Right? So I think personally, I think I'm more of a realist. I want to believe that there's something more, right?
Yeah, I agree. This other version is like some subtle shoved out in calculator, but more subtle. Did not say shut up, say something else, like calculate.
Yeah. And I mean, I truly believe that there's nothing wrong with taking that sort of mentality to move on with your life. But if you want to have discussions about what does the wave function really mean, then that approach is just what's even the point of talking to someone that says you can't understand anything other than what you can measure.
Yeah. I mean, this approach brings a lot of things, good things, but I mean, a lot of technology, all the things that we have. But it's valid, but I mean, more the philosophical part, it's like vague.
One thing I'd like to learn from the physicists or someone else is what is meant by an effective theory. Or just in terms of today's discussion, is the von Neumann formalism of quantum mechanics, is that an effective theory or not?
Yeah, I don't know what the term means, effective theory.
You mean that it's like a theory, like thermodynamics? That's not a.
Yes, that's a good example.
Not a fundamental theory, but it's not fundamental, but it has. I don't know, because you have like fundamental particles that obey like quantum mechanics rules. So.
Yeah, that might be a good example of what is meant, in that classical thermodynamics isn't, so to speak, invalidated or shown to be wrong by statistical mechanics, but the statistical mechanics shows how the classical thermodynamics emerges from the statistical mechanics model. So that might be similar to the relation between quantum mechanics and classical mechanics. I don't know. That's why I'm asking the question.
Yeah, I don't know, because I'm thinking like particles physics. You have like fundamental particles, and your quantum mechanics. You need quantum mechanics, like quantum field theory, to explain. I heard some people believe that gravity was effective, could be effective in this way. That's why it's so complicated. Would be so complicated to quantize, like, since like the gravitons, like the fundamental would be like the fundamental particle of the gravity was never detected. But at least in my belief, I think it's just a matter of technology. We just detected like gravitational waves like 10 years to have like very sensible particle associated with this wave. It takes more time, I think. But I think none of them are really effective in this way, like in the modern dynamic way. But I mean, it's just, I don't know about, you said like von Neumann has some suggestion about this?
No, I was just checking my references that von Neumann's proof excluding local hidden variables was in the 1932 Foundation's book.
Oh.
And that's, to my understanding, that's what Bell is deriving his inequality from, but I must confess I've not yet managed to understand Bell's paper.
If I remember correctly, there was a mistake in von Neumann's proof.
Oh, yes. Oh, that's good.
That's
it-
what Bell kind of uncovered, I believe.
You're right. I forget the name. That would be a good subject for a little talk, because I believe part of the issue was that it was a woman and not very famous.
I see.
See if I can look that up. Oh, that Greater Hartman. And that she wrote a paper in 1935 that Bell referenced. Yeah,
Interesting.
let me put that in the chat. I want to look that up. Yeah, thank you.
Yeah, I believe the argument was that von Neumann had a proof that general hidden variables couldn't exist. But
Yes.
then Bell was obsessed with this concept of how come Bohm had this whole pilot-wave theory that has hidden variables. Now they're non-local, right? Non-local hidden variables. But von Neumann proved that you can have hidden variables, and that's why Bell started looking into this whole thing and came up with his inequality.
I think the crux of the matter is that von Neumann thought he'd disproved all hidden variables, but he only disproved local hidden variables.
Correct. Yeah.
I need to look up this Greater Hermann because that's pretty amazing. But Bell references the Greater Hermann paper. But I'm unfortunately at that point above what I understand. I mean, thanks to Carlos, I'm beginning to understand some very simple things about the physics. But I need to the point where I can read, say, the EPR paper. So that's incredibly helpful. I hope further down the line that I can read Bell's paper or von Neumann's and understand it. So I'm very appreciative to the community for educating me.
Yes, so what do you guys think next? Should be about like the Bohm, or we could go to Bell, don't respect the history, or see David Bohm. Did have some discussions? You guys know what you prefer.
Yeah, I like this this approach that you proposed last
Like
time we
the
met of
history.
following the history. I
Yeah.
think it's a good idea.
Yeah, okay. So next I'll bring something about David Bohm's paper. And maybe we could have more than one like lecture to show some, show some calculations. Maybe, I don't know. Today I didn't show because the things was like simple, or just the idea. It's nothing. But maybe in Bohm's, I'll try to understand and see what's the difference. What's this? Okay, yeah. I remember the last time when we was discussing about the spin. Yeah, they have in the Bohm, they have like they try to understand the things related to spin and Stern-Gerlach experience. They have. I just looked after that day, and yes, they have an explanation. I mean, the interpretation.
Yeah, I would think so, because Bohm also wasn't Bohm the one who took Bell's inequalities, and no, sorry, Bohm was the one who took EPR and adapted it to spin, right, to make it easier to understand.
Yes.
So you would think that his pilot wave theory would have also been well explained for spin, since he understood that well, right?
Yeah. This is in his book, I think 52 book about quantum mechanics. 52 or 51.
Okay, unfortunately, I have to get going, but thanks again for the great discussion.
Yeah, well, I just finished. So I would like to thanks George, Bob, you, Diego, Barry, and everyone that is watching. Bumblebee, I don't know, Bumblebee is still here.
If I
But
can, well, thank you, Carlos, and thank you, everybody who contributed. I'd like
Goodbye.
to suggest that maybe we have shut up and calculate during the day, and then at tea time we are allowed to chat.
yeah. Every 50 days,
Great
we chat.
suggestion.
Yeah. I would like to make an announcement, actually. Just a reminder, I will send this. So it's on the 15th. We will use, I know Quantum Tea is held on Tuesdays, but on this occasion, we will have a special session on Thursday, on the 15th of January. Sorry, February. It will be some sort of like a presentation and then followed by a debate by an author of this paper. I think some people, if you are on the quantum circles, you probably heard of this paper. Recently, it's called the Quantum House of Cards. It's a constructive critique of the state of the industry, of hype, and so on. Yeah. So we'll have the author Javier to come and give a talk, a presentation, and then we'll open up the floor for like questions and have like an open, constructive debate about the state of the industry, the expectations and so on. Yeah. So I will be sending out invitations once I set up the actual event thing, and it will be held at 6 p.m. UK time. So yeah, that's one of the reasons I said we decided to not put it on Tuesdays, because Quantum Tea is at 5 to not disrupt the the time. So this is Quantum Tea extended. Yeah. That's maybe that's why we should call it Quantum Tea extended. Yeah. So yeah. So you are all welcome to join the debate. Constructive, as I was putting, even those of us who are positive about the technology, it's good to have different opinions about the state of it, the reality versus hype and all this type of stuff, which doesn't help the actual industry, to move forward. Criticism helps, this is the thing. So constructive criticism, which I think this author has done a fantastic job in doing so. Yeah. All right, so that's it. That's all I wanted to announce. So yeah, Carlos, maybe you can stop recording, and if anybody else wants to say anything.
Okay, so I stop recording. So people from YouTube, thanks for watching. And if you are not here in the live section, please appear and give us your opinion about this stuff.
Yeah, and don't forget to give us thumbs up YouTube for the algorithm to help discover more this debate.
Yeah. Okay, I'll see you probably not next Thursday, in the 13th.
Yeah.
I think.
So we'll have one.
But we are not.
Yeah.
Yeah, we are. Okay, see you guys. You guys from internet.